Welcome, PCS members and friends, to our today PCS IBS seminar. It is a pleasure to host today with us Dr. Cheolhee Han from Tel Aviv University. And our scientific host today is Sung-Hoon, and I ask Sung-Hoon to introduce our speaker.
Yeah, thank you very much. I'm pleased to introduce our speaker today, Cheolhee Han. He completed the PhD degree in 2018 at the KAIST on the study of the signatures of non-Abelian braiding in a fractional quantum Hall interparameter. After the PhD defense, he stayed at the KAIST 2 years more, and then moved to the Tel Aviv University, the group of Professor Eran Sella. So he's currently interested in some strongly correlated systems like the Kondo systems, Fermion Kondo lattice systems, and the fractional quantum Hall systems, spin liquid system, more systems, and mainly focusing on some exotic properties of these systems, like quantum correlations, entanglement or coherence, and how to measure these correlations in experiment. So recently, in collaboration mainly with Eran Sella and Igal Maya and Ben Gurion University, he did some nice works which will be presented today with the title Measuring Exotic Entropy in the Mesoscopic Systems. So he will stay today and tomorrow. So if there's someone who wants to discuss with me, please visit our digital room. So let's welcome the speaker.
Thank you for introducing me, and thank you very much for inviting me here. Okay, my name is Cheolhee Han, and today I'm going to talk about measuring exotic entropy in the mesoscopic system. This word exotic, I'm quite sure that all of you are quite familiar with the concept of entropy, but
Probably you can use that.
Oh, yeah. Old fashioned. I like old fashioned. You do. Now it works. So the word exotic looks a bit ambiguous, and I like the other word, fractional entropy. So the outline is very easy. So I start with introduce. Maybe all of you are quite familiar, but introduce with entropy and entropy measurement in the mesoscopic system, which is a bit new. I explained some recent experiments, very brilliant experiments. And then I introduced some concept of fractional entropy. The word fractional looks very weird because entropy is a kind of a logo of some number, but I introduced it. And this fractional entropy is related with the concept of anyons, and anyons naturally connected with some kind of topological quantum computation, which is one nice keyword of this area. And then I briefly mentioned, I explained how to measure this fractional entropy in the multi-channel Kondo system, which is one kind of exotic systems. And then, if possible, I explain something more about entropy of fractional quantum Hall system, if time allows. And then I summarize the results. Okay, entropy is usually we say that entropy is a measure of randomness, and or more precisely, I think, is a measure of accessible state. So it is written like this: log of some omega, possible number of possible state. And then, so if you have two quantum dots or two quantum pairs, and if they are weakly tunneled. Yeah, I used old-fashioned. They are weakly tunneled. Then these two states are almost degenerate. If there is one electron, then this electron can be here or there. So it's a 1-0 state or a 0-1 state. So there are two ground states, and the entropy is log 2 because there are two accessible states. But if the tunneling strength becomes larger than some energy scale such as temperature, then in this case, the eigenstate of this Hamiltonian is some combination of this 1-0 and 0-1 state, which I call the even and odd state, whose energy eigenvalue is plus gamma and minus gamma. So if this gamma, as I said, if this gamma is much smaller than temperature, then entropy is log 2. But if gamma is much larger than temperature, then the entropy is log 1 because there is only one ground state, one accessible state. So it's 0. So now I will introduce how can we measure this very small number of entropy, because the entropy is in the most of the systems are quite large. So I want to introduce some recent brilliant experiments here.
Sorry, may I ask you a question?
Yep.
You're mainly interested in the entropy of the ground state.
Yes, the ground state or the entropy of the state. Entropy of the system. Entropy of the system is that accessible state is that if you have some state inside the temperature range, then there is these states are accessible. That's what I mean. So it means that if there are two states inside the temperature, then entropy is log 2, and if there is only one state in the temperature, then there is only one state, the log 1, which is 0.
I keep saying, do you consider the topological state?
Yes.
If we think about the zero temperature entropy, the relate of some topological one, assume the order state in the think about the unknown.
Yes.
Unknown theory and second the order parameter well defined.
Yes.
But some system is
Some topological system.
topological.
There is topological degeneracy.
FPT, for example, this kind of entropy also you are consider one.
I will discuss about similar thing if time allows. And if time is very short, then we will discuss later today or tomorrow. Okay, so I first introduce some recent experiments. Okay, you know that from the thermodynamic relation, the entropy is minus of df dt. Df is free energy. And also there is another, from the free energy we can derive more observables, such as number is minus of df d mu, some chemical potential. So from these two, then we can write this relation, which is Maxwell relation. This is quite familiar with us, but then from this we can make, by integrating this right-hand side, then we can write the entropy difference of two different chemical potentials as measuring the temperature derivative of number along the chemical potential, say mu0 to mu1. Then this is their measurement device, and they want to measure the some entropy of this small quantum dot by putting some heat fast and the number measuring device quantum point contact like this. So it looks like this, okay, basically. So there is quantum dot, and if there is 0 electron inside the dot, then there's only one state, empty. But if there is one electron inside the dot, and if it is spin-full, then because of spin degeneracy, there are two degenerate ground states. So now its chemical potential changes to mu1. So using this Maxwell relation, we can measure by measuring this d and dt of this quantum dot, we can measure the entropy difference between this and this state.
Sorry, question.
Yep.
The Maxwell's relation that is partial derivative.
Yes, it's basically it's a partial derivative. Yeah.
So the n, what are you keeping constant?
So in this case, n is constant of n is
So
constant
S is
of
the function
temperature.
of what and what? S is the function of mu and t. Is that how you were thinking of it?
Yes, S is function of mu and t, and n is function of t. Yeah, also mu and t. Yeah.
So you were keeping t constant while
Yeah, while integrating this, yeah, I keep t constant here.
but if you keep t constant, how can you take derivative with respect to t?
Two different temperature and measure number and make derivative. So for the one the number is to define the number, we fix the temperature, but we can define the number for different temperatures. So we can define the derivative of temperature derivative of number. So okay, this is the number for two different temperatures. That the sharper one is the lower temperature and the ruder one is the high temperatures. Then we can obtain this d and dt. This is all theoretical curves. This is what I computed. And then you can see d and dt looks like this. And okay, so by integrating this d and dt from some chemical potential mu0 to mu1, we can obtain the entropy difference between this state and to this state. I will show you. Okay, so this is the entropy difference. Here, initially, there is only one state, and it goes to the log3. Log3 because there are three degenerate states: empty, and spin down, and spin up. And then finally, it goes to the one electron state, which has log2 state. This is all theoretical curves, and what they measure is quite interestingly. It goes to almost exactly log3 and approaches to the log2 and saturated. This is experimental data.
Essentially, they measure levels. Right? You could also do the same thing without the notion of an entropy.
Yeah.
So
but
basically, what they see is that
yes,
the number of accessible states
yes.
changes upon varying
Yeah.
the gate voltage. Can you explain, please, so the setup top left figure? Why are there? What is this left box meaning? So
Left box.
So the dot is in the right box there, right?
Yeah, that is in the right box.
So what do you need in the left box?
Since I'm not an experimentalist, I can maybe my explanation is a bit weak, but up to my knowledge, this box they want to make this d and dt, so they want to make a very small temperature change by putting some current. To apply some current, they claim that this best up to my knowledge, this best is quite large.
So this white stripe which separates left
Yeah,
and
so
right parts is just saying that it's a long thing.
Yeah, it's saying that it's quite larger.
So
thing.
there's some kind of weak small temperature gradient.
Yes, that's what they want to make, and they claim that they made it.
And how long is this longish?
I'm sorry,
Because we see some scale there, 500 nanometer. What about the red part?
I'm sorry, I don't know about the experimental parameter, but up to my knowledge, is quite long to make a very small temperature gradient.
And why do you actually need the small temperature gradient? Because at the end of the day, you just connect to this dot. So why should I care about how the temperature gradient in this huge red bulk of the setup?
In fact, this is the up to my knowledge, this is the first paper to measure the entropy of the log2, and now up to my knowledge, in this paper, as I know, they do not use very large bets. Their up to my knowledge, their best becomes a bit smaller. But why they want to make small delta t? Because they want to avoid some other possible side effect because of the large temperature. If for example, if some other experimental guys use quite large temperature deviations, such as 10 millikelvin or few order of 10 millikelvin, and then they say sometimes they measure log 2 or log 3 quite well, but sometimes they measure with different values. So and then they cannot. Then they try to make the temperature deviation very smaller and smaller. So that's the kind of answer.
So, you don't change the chemical potential, right? Or
in experiment, they change the chemical potential. I don't know where is the chemical potential, but yes, in this case, I want to show is that chemical potential is starts from some kind of mu0 to mu1. And they measure it needs to measure this dNdt along the chemical potential.
okay. So they're changing mu and T together?
They measure two temperature and they along the old chemical potential. This resolution is also quite important, I think.
So what they're doing is that they stand at one chemical potential, then they change two close by T's.
Yes.
And that calculates this D and dt, and
yes.
then they move.
Yeah, in fact, up to my knowledge, they basically set one temperature by using this device and measure along the chemical potential and set different temperature, which is larger or smaller, and measure the number along the chemical potential and make the dNdt like this.
Thanks.
And this is the usual way up to my knowledge.
So basically, the long middle just to make sure that the particle before coupling with the dot will have the desired temperature that you want, right?
Sorry, I'm sorry.
So it's a very long. Yeah.
This long bass.
Just to make sure that before coupling with the dot,
yes,
the breaker has the temperature that expects that desired.
Yeah.
It need to take time to get this
yes.
temperature, equilibrium temperature.
Yeah.
Before contact with the.
Yes, I think you are right.
But then couldn't I also simply, maybe not, but I was thinking about just the varying some gate voltage, do the standard quantum dot experiment with the gate voltage, which controls what is how many states there are in the because these states are the states in the dot, right?
Yeah, this state in the dot. Right. Yeah.
But I think temperature is important because you want also to have to distinguish between 1 and 2. Okay.
Yeah, some other excitations in the bulk, and they want to remove all the things.
And then in this case, you do not change the chemical potential on the left, but we can change the chemical on the right. So basically, the key point that's a different chemical potential can use the VP to change.
Yes, in fact, yeah. Yeah, this is in fact it's not the chemical potential, it's the on-site potential.
So you can change on the left, you can change on the right,
same thing. Same thing, yeah.
So one question. So when you explain it with the picture of the dot, so there I understand when you talk about mu1, you have no particle, and when you have mu0, then
there's no one particle.
There's one particle. So then it seems like your mu, if I'm looking at the dot, then I can only see discrete jumps in the chemical potential. How do you see the whole?
Yeah, but everything is in some equilibrium, so it means that there are some portion. That there is say it's kind of Fermi-Dirac distribution. 1 plus the one divided by this number. In fact, is 1 divided by 1 plus 2 e minus beta epsilon or something.
So on the dot, there is like some fractional number.
Yeah, so if you lower and lower the temperature, then it becomes almost jump and it becomes very sharp thing and goes down something. This is all the temperatures.
This number is only electron.
Yeah, this number is only electron number. Yes. That's why they want to make the small temperature range to avoid the other environmental, such as environmental effect. Okay. Oh, sorry. So now I will introduce the most weird part of this talk, the concept of fractional entropy. This fractional looks very weird because, as I told you, this goes to if you know some state, then it is log 0, log 3, or log 2, or some log of integer. But there is some kind of fractional entropy, which is the signature of some non-locally stored informations. And and usually this related with the why it looks like that. Okay, it's good. Related with concept of anion. Maybe some of you are familiar with anion, but some not. So this anion is a fractional excitation. This is the most important information. So one example of this non-local information is that there's a kind of Majorana germos. So this is the famous topological superconductor system. This is the topological superconductor system, and we know that people claims that at the edge of the topological superconductor system there appears Majorana germos. And also another platform is the multi-channel Kondo system. And in the multi-channel Kondo system, this is the multi-channel charge Kondo system, which is realized in the French group. And in this system, and in the dot, there is some fractional excitations, such as Majorana germos for 2-channel Kondo, or Fibonacci anions for 3-channel Kondos or something. And another example is the topological ordered phase, which is such as fractional quantum Hall system, which host anions inside the system. And today I focus on the first part, but if time allows, I briefly explain about the second part. And in this system, there appears this fractional entropy. I will introduce why. Okay, first I briefly introduce Majorana fermion. Maybe all of you are just at least heard about this. And if you have one spinless electron, then there is the Hilbert space dimension is 2, because we can make state like 0 empty state or occupied state. So its entropy, its corresponding entropy is log 2. So this is a conventional fermion operator, which is complex, and we can define two Lear fermions, which is 2 Lear Majorana fermions, like this. And then these particles are Majorana fermions, and it is antiparticle of their own particles. So this is the known thing. So it means that this one electron occupied or unoccupied state or empty state can be written in 2 Majorana fermions. So naively speaking, then these 2 Majorana fermions can form two states. To the space dimension, Hilbert space dimension is 2. Then naively speaking, if we have 1 Majorana fermions, then the Hilbert space dimension must be square root of 2. So if we can measure the entropy corresponding to this 1 Majorana fermions, then its entropy is half log 2. This is what people call the fractional entropy. Then how can we realize it? Realizing means that how can we realize it on the system, and how can we measure this fractional entropy? And is it real or not? So to explain it, yeah.
1 Majorana state you cannot think of it.
Yes, that's the point. So it means that 1 Majorana fermion is a bit weird word, but in some systems, using some trick with continuums, and that's what I will tell you. And using some tricks, we can make one Majorana fermions, one localized Majorana fermion and one delocalized Majorana fermions, which we cannot detect. So, okay, I will explain it later. So to explain the Majorana fermion, the most easiest model is the Kitaev chain or topological superconductor systems. So if you have two dots, which we can write four Majorana fermions, and then if you make some hopping between two dots and some pairing between two dots, and at some sweet point, this combination of these two Hamiltonian is written in the coupling of one Majorana fermion in the first side and another Majorana fermion in the second side. So in this case, this eta 1 and this gamma 2 are free. And do it again and again. Then you can make this eta 1 at the one side and say times L times, then at the gamma L at the other side. And you can make it very far. Then these two very long, very distant Majorana can form one Lear fermions, or two Lear fermions, one Lear fermions and this dagger. Then we can define the number operator of these Lear fermions, and you can see they form a two degenerate state. So in this system, the entropy is log 2. This is usual. And you know that these Majorana germals are quite popular because of their another exotic properties, which is non-Abelian braiding properties. And using, in some ways, if we prepare two pair of Majoranas, then we can set their initial state as 0, 0. It means that they fused into the 0 state and they fused into the 0 state. And if one Majorana braid the others like this, then their final state is up to some phase, the 1, 1 state. So it means that, and of course, 0, 0 and 1, 1 state, the overlap of the 0, 0 and 1, 1 state is 0. So it means that using this braiding, they can change the state, or then we can say these Majorana fermion, Majorana germals are for the non-Abelian anyons, because the state changes. It means that their statistics are non-Abelian. So because of these non-Abelian statistics, this is quite appealing keyword of the topological quantum computations like this. I don't want to introduce this in more. So, and one smoking gun is the fractional entropy of this one Majorana, if it is possible. I will explain. Okay, before doing this, I want to make some side comment. Okay, I want to explain some maybe familiar, maybe very easy model, the resonant level model. So if there is one level which couples to the continuum. Continuum means that the level spacing of the system is much smaller than the temperatures. Then the Hamiltonian looks like this, and if we neglect this on-site energy, then their free energy looks like this. Because it is continuum, we can make it to integrate, and the density of state is just some constant comes from this continuum leaf, and some Lorentzian function comes from the coupling between the dots. And you can see if the tunneling stress is much smaller than the temperature, then this Lorentzian becomes just delta functions. So entropy is because of this delta function. If we put this onto here, then you can obtain the log 2. It is quite trivial because this level is occupied or not. So there's two states.
So but in this you have the interfunction when the tunneling is smaller than the energy rather than the temperature, right? The equation that you have.
Yes, in this equation. So
basically, you have the interfunction when gamma much smaller than epsilon rather than much smaller than t.
Yes, much smaller than epsilon, but you know that during from this integral, in fact, if you consider this integral, if the epsilon is larger than temperature, then it is they are meaningless. So that's why I say the temperature, not epsilon. It's okay. And if another example is that if you have a very larger coupling, tunnel coupling, then in fact this level is effectively absorbed into the continuum like this. So in this case, the density of state is just this constant. Constant comes from the continuum lead, and just if gamma is infinity, then there is 1 over pi gamma, and which is very, very small because we assume the gamma is very large. Then in this case, entropy is just lead entropy. There is no log2. So log2 disappear. This is, in fact, you know that this is quite trivial example. And we know that if you lower the temperature much lower than the delta, then this log2 reappear. So this is a bit tricky, but you know that there is log2, but in this limit we cannot see.
Sorry, may I
Yeah.
question the density of stage?
Yes.
The stage of the total system or the density of the is the lead?
Total system is
Total system.
this level and this lead.
I see.
So this lead, the density of state of lead is just, I assume this is constant, so it's just constant, and the density of state comes from the additional level is written in this Lorentzian.
I see.
Yeah. So I put this formalism into the Majorana topological superconductor or Q-type chain. Then this model becomes to the Majorana resonant level model, which is a Majorana version of the resonant level model, written like this. This gamma L and eta K are all Majorana fermions, and this eta K satisfies this computation relation. And this tunneling strength is proportional to this J square. And okay, then let's see what happens.
I question eta K is one Majorana operator.
Eta K is one Majorana operator, but
why one Majorana interact in one electron? How to
one Majorana interact with one electron?
Gamma is one electron.
Oh, gamma and eta are all Majorana fermions. Majorana fermion means that
how to operate the one Majorana in the level? Is it possible? Are they computed? One Majorana bound state can be realized.
One Majorana bound state can be realized. That's the question, and I can answer if the experimental idea. It is possible because that's what I explained. There is two Majorana fermions on the bound, and at the boundary there's only one Majorana fermions, one Majorana bound state. Is this the answer of your questions or?
I think the question is that how the single Majorana at the end of the nanowire couples to the electron in the lead.
Yeah, but you know that since they are very far, very far. So if there is a tunneling because of this gap, tunneling and pairing, then this electron and this electron inside the dot can tunnel.
Majorana is charged electrons.
Yes, they are basically charge neutral state, charge neutral particle. Yeah, but charge neutral particle means that there is no charge. It means that, up to my knowledge, it is hard to define the charge of Majorana.
Where there is only electron can be possible in the charged state. And this H is a non-charged state. How to
Actually, the short comments is that you can write the tunneling Hamiltonian in a general form. The field operator, electron field operator of the superconductor, and coupled to the electron in the lead.
Yes.
And then you simply rewrite the field operator in terms of the Bogoliubov operator, including the Majorana, and then just the low energy approximation when only the Majorana level is dominant, then you can effectively define the tunneling Hamiltonian between the Majorana and the
actually
electron.
additional term is immediate. You assume some limit is this additional term is coupling from only coupling is likely.
Yes,
high order term is
there is higher order term is that higher because you know the fundamental in principle the term looks like CL dagger and CL dagger and CK, but from this pairing and since we assume this pairing and tunneling gap are quite large, so this part cannot participate into this process. So only this Majorana part looks like only this Majorana part tunnel to the lead. So yeah, that's the answer. It's my answer. So
sorry, just to understand. So in your Hamiltonian, first term is the tunneling between Majorana H state and continuous lead.
Yeah.
And second term is simply kinetic energy of
the leads
written in Majorana form.
Yeah, and I omit another Majorana forms because in this lead can be written in terms of two Majoranas for single energy, but I omitted. I'm sorry.
Okay, it's a function of K, but you wrote spin index and some.
Sorry. That's my mistake. I'm sorry. I forgot to remove it. Sorry.
Okay.
There is no sigma and no J. Sorry about this.
I computed in the rate.
Yeah.
Already the charge neutral creation is.
You know that
one electron and one hole is a single channel.
At the pair, if you consider some kind of pairing, then you can make the Bogoliubov operator. Then we can ask that what is the charge of the Bogoliubov operators? It's at the sense of the chart, at the viewpoint of the chart, it's the same. So it is hard to define. We can say the occupied state and not occupied state are some linearly combined or something. So in this,
so the lead should be superconductor.
Sorry.
So the lead should be superconductor.
No, lead can be normal lead. Yeah, because this gap is very large. Since this gap is very large, then the normal lead tunneling can be written in this form. Now, if the gap is very small, quite small, then there appears some other
small and large compared to what?
Smaller than the maybe temperature. Maybe temperature, I think. Then there appears eta R over n gamma k. But I omitted because I assumed that this gap is, in fact, in this case, the largest standard scales, larger than any other things. So in this case, we can write free energy whose density of state is written like in this form. I will explain the part by part. Here, the C is the same thing. C comes from this continuum part. And this half of delta comes from the decoupled Majorana fermions. And this Lorentzian comes from the coupled Majorana fermions. So if you assume that this tunneling is very small, usually as usual, is tunneling is much smaller than temperature, then this Lorentzian also becomes the delta functions. So it is half delta makes full delta functions. So it gives log 2. It is what we know, because this topological superconductor can make a log 2 degeneracy. But if this tunneling is quite large, then this Majorana fermions is absorbed. Because of this large gap, in this case, different from the just a simple resonant level model, not a full resonant level model, full level goes absorbed into the lead. In this case, only one Majorana absorbed into the lead. Then, in this case, this Lorentzian becomes 1 over 2 pi gamma, whose gamma is quite large, so it's almost 0. And the entropy comes from half delta, it's just half log 2. That's the origin of the fractional entropy. And this is the way to see this fractional entropy. And of course, as I said before, if you lower the temperature much lower than this continuum level spacing, then you can finally detect the hiding half log 2. So it gives finally some lead entropy and log 2 entropy. So this is the trick. So if you larger the temperature, if you make some temperature larger than the level spacing, then you can hide half of the Majorana fermion into the lead, and you can only see this half of the Majorana fermions, only single Majorana fermions.
I beg forgiveness.
Yeah.
In the superconductor, normal metal is contact with the
Yes.
underlying reflection is appear. In this case, this is
Underlying reflection is if it is a trivial superconductor, there is underlying reflection. But in this Majorana fermion system, there can be some tunneling of Majorana fermions.
underlying reflection energy is more, right?
In this case, I assume that.
This is a zero mode.
Yeah. Because this is zero mode, and I assume that this is in the real system there might be some kind of boundary reflections, but I assume quite ideal systems. So in this case, there's only Majorana tunneling like this, and due to this Majorana tunneling, there appears half log 2. Okay. Then now we know that the half log 2 appears and sometimes log 2 appears. And then now I will tell you that how can you measure this half log 2? To do this, we first put a quantum dot near this junction. And then add another continuum lead which have a gate voltage, the chemical potentials, and there is a device which measures the charge of this dot. And since this dot is empty, there is no Coulomb interaction. So the tunneling is quite large. So this Majorana fermion is absorbed into this lead, and there is half log 2. And if there is one electron, then because of this electron, they feel some Coulomb interactions, and they can be distant. They will be distant like this, or in this direction. So this tunneling strength becomes weaker and weaker. And also that, so finally, if you put some number of electrons inside the dot, then finally you can make half the log 2, and there is a lead entropy still. So this is some theoretical calculation, and we assume that if you put 3 electrons inside the dot, then this tunneling strength goes to 0, almost goes to 0. Then you can see this is the number, and this is the to make the DNDP for 2 different temperatures. And they finally get this kind of delta S. Delta S chemical potential is some relative entropy, which goes to the half log 2. You know that this is the half log 2 line. It approaches half log 2. And this peak comes from the degeneracy of this dot. There is almost log 2, slightly larger entropy. So, okay. So, you know that by integrating the NDT of this quantum dot along some chemical potential in this system, we can obtain this fractional entropy. In fact, this fractional entropy, we can say more precisely we can, and by measuring this, we can say we measure the quantum dimension of Majorana zero mode. But the point is that this topological quantum superconductor is still a bit controversial. So I want to make another system, which is the charge Kondo system.
Sorry.
Yep.
So if I consider temperature T equals to 0,
yes,
then plot B would be completely.
It becomes log 2. So in fact, in this paper, they say that if temperature is lower than as I told you, lower than the level spacing of this lead, then it finally goes to the log 2.
And what happens between mu equals to 1 and 3?
I'm not sure, but as I understand that it becomes just log 2 and goes 0 and log 2 and goes 2. It might be because everything is log 2, so the difference is 0. So I briefly explain about the charge Kondo because there is no time. So the Kondo system. So you might know that single channel Kondo system. Single channel Kondo is the quantum impurity is interact with the continuum lead. So impurity spin interact with the continuum lead at some point. And so this part is the spin flip interaction part. And because of this spin flip, in this single channel Kondo model, the ground state is Kondo singlet. But if you have one more channel, if you add one more channels, then this impurity spin can interact on the left side and right side, like this and like this. So they cannot choose one of them as a Kondo singlet. So there is a frustration. So, and also if you apply some magnetic field on the impurity side, then it prefers if you put the downside the magnetic field, then the impurity prefer to the downward spin. So it may finally makes a single ground state. So this H makes the frustration weaker. And one important thing is that this model can be mapped into the Majorana resonant level model, which we discussed a lot. But in this case, I wrote this Majorana fermion as gamma D, and this Majorana fermion can be coupled to another pair of Majorana fermions. And the most important thing is that this system is realized in the charge Kondo setup about this one Nature and one Science paper in this setup. So I will briefly introduce about this new Majorana resonant level model. So this this term is the interaction of one Majorana fermions to the lead, and this H term is the coupling between the one Majorana fermion the other Majorana fermions. So, and if we first neglect this H or on-site energy of the Majorana fermions on the resonant level model, then the free energy and the density of state is, as I told you before, it looks very similar. Constant comes from the continuumly, and half of the delta comes from the decoupled Majorana, and the Lorentzian comes from the coupling. And if TK is very large, then this Majorana effectively absorbed into the lid, and this density metric, the density of state, goes to the constant plus half delta functions, and the entropy is half log 2. But in this, and then after we absorb this one of the Majorana, then we can turn on the magnetic field H. Then again, the density matrix, the density of state, can be written like some constant plus some another Lorentzian, which comes from this magnetic field interactions like this. Then, if you larger the magnetic field, then again it goes to the negligible contribution, and the entropy is just lead entropy.
I'm sorry, a question. So you have Majorana fermions only when you have level of degeneracy on your quantum.
Yes.
I mean, if you turn on magnetic field or gate voltage, you will leave.
That's the thing. That's the simpler version of this complex.
I mean, then it's not clear how one Majorana fermion can be absorbed.
This Majorana, so it means that if you larger the magnetic field, then what you say is that the degeneracy is removed and you cannot detect this loop. Yeah, so there is no loop. So then we can say that by changing the magnetic field, or in this case, gate voltage of this in the metallic dot in the charge Kondo system, then we can measure the half log 2. I will show you the pairs. So the answer. So here we assume that the Kondo temperature is much larger than the temperature, and there is a finite magnetic field comes from the gate voltage. And this is the phase diagram of the this is entropy of the two-channel Kondo system, two-channel charge Kondo system. And by changing the gate voltage, this 0.5 is the spin the charge degeneracy point of this last dot. So in this point, there appears two-channel Kondo system, two-channel Kondo phase. And if you have 0 or 1, then at the low temperature, then they prefer empty state or occupied state. So I want to see the entropy difference between these two different gate voltages of this light dot. So if you lower the temperature, then it goes to the half log 2. So this is what we can see. So it goes, if you measure the charge of this light dot using another quantum point contact device, and you measure the dNdt of this dot, then you finally obtain this kind of graph, which approaches to the half log 2. So in this case, half log 2 is measurable, and I didn't show you, but if you apply one more channels, then you can measure the log of Golden ratio, which is a signature of Fibonacci anion, which is more exotic particles than Majorana germans. Okay, I think I have 5 minutes.
Sorry, one question. So on the previous slide, you explained us that you use this probe or quantum dots to couple coupling between Majorana fermions and lead.
Yes.
Series of superconductor.
Yeah.
So here you couple your probe with what? With large quantum dot?
Yeah. Large quantum. So sorry, I didn't listen to your question. So please.
I mean, in your previous model, you use probe quantum dot to change the tunnel matrix element between fermion and continuous spectrum.
Yes.
What you're doing?
Why? So you mean that why we measure this charge of this dot?
Yeah, I mean, what's the role of this probe coupled to quantum dots?
Okay, I will explain. In this case, I want to say that if you change the magnetic field of this impurity, you can see this change of half log 2 and 0. Then this the magnetic field, the corresponding to magnetic field corresponds to the gate voltage of the charge Kondo. So I want to say is that if you change the gate voltage from some 0.5, which is the two-channel Kondo limit, to the 0 or 1, then you can see the entropy difference. So in this case, I don't want to put another quantum point or not another quantum dot between some point.
Okay, so it's just gate electrode.
Yeah, just gate changes the number and number of occupation of this large dot, and we just measure this occupation of this large dot. Yeah. Then finally we obtain this entropy difference. So this is the end of the first story, and I will tell I use my 4 minutes to explain the details of some entropy of the fractional entropy in the topological system, fractional quantum systems. I briefly mentioned it. In the fractional quantum systems, there appears this anyons. They host this kind of anyons, which is initial state is different from the final after braiding state. So in this case, because of this presence of these anyons, there appears topological entanglement entropy, which is the key diagnostic of the topological ordered phase. And entanglement. Why it's like this? Sorry. Entanglement entropy is the entropy of the reduced system like this. And in the topological systems, this entanglement entropy can be written in the linear part of the cutting side and some subleading part, which has subleading and negative, the minus of the positive part. And this gamma is what we call this topological entanglement entropy. And topological entanglement entropy is defined like gamma is a log large D, and this large D is we call it the quantum dimension, which is the sum of all quantum dimensions of anion which they can host. So this is the details, and I want to tell you that for the one-third system, this topological entanglement entropy is half log 3, and if you have nu equals to 1, then there is a 0 topological entanglement entropy. So my question is that, is there any relation between this gamma and thermodynamic entropy? And surprisingly, there is a relation between the thermodynamic entropy and this topological entanglement entropy. This is quite surprising because usually entanglement entropy and thermodynamic entropy are very different quantity, although they share the name of entropy. But in this case, in this topologically ordered phases, I want to say that if you have one single drumlet, or say there is a very weak backscattering in the topological ordered system, and if you split the one topological drumlet into two, then the entropy difference between this single drumlet to the double drumlet is the same as the topological entanglement entropy gamma. There is some deep relation from the CFT calculation, but I don't want to mention it, and I just give you some very brief intuition. So why it happens like this? So in this single drumlet case, some anions and is anti-anion. Anti-anion means that the one anion the final state must be vacuum. Some anyons and their anti-anyons can be located along the left side and the right side, but because the total topological charge of this droplet must be trivial, so this kind of left one electron inside the one droplet and one anion inside one droplet and another anion inside another droplet is prevented because of some super selection rule. So it means that this UV limit or single droplet case is more uncertain. It means that it has more entropy. That's the very brief reason. So I want to briefly say that this entropy difference between this UV or weak backscattering limit and the strong backscattering or splitted system, the entropy between this and this can be measured using this kind of device. We add a quantum dot as usual, as we did in maybe 3 times, and then measure the charge of this quantum dot. And you assume that if you put kind of 3 electrons inside the quantum dot, then because of this interaction, their tunneling becomes larger and larger, and finally it goes to the strong backscattering case. Then, using this Maxwell relation, as usual, we can obtain the entropy drops like this. If you see the nu equals 1/3, then it approaches to the minus half log 3, minus log of square root 3. And I want to say that this can be applicable for all the topological at least chiral systems. And this is the first question of you, means that this is the entropy change due to the topological change, topology change of the system. So yeah, I didn't mention. So in this sense, this topological entanglement entropy is also measurable using the same sense, using this thermodynamic Maxwell relation. Okay, and this computed using the thermodynamic beta answer. So this is my conclusion. The fractional entropy is signature of non-local information, which is the non-Abelian anions or topological ordered basis or something, and it is measurable using proper charge measurement. And this is my collaborators, and thank you for listening. Yeah.
So the intuition that you provided for topological entropy, that works for non-Abelian systems?
Yeah, similar works for the non-Abelian systems. In fact, this is not proof. This is just a very short argument.
But they have the proof?
Yeah, in this paper they proved this. And they used some CFT argument using some modular transform, and then it is not very difficult for. Yeah.
And the picture that you showed there, the half, nu equals half. No,
Nu equals half. Yeah, nu equals half.
That's assuming Abelian or non-Abelian?
I assuming the Abelian. So because nu equals half is a bit tricky, because nu equals 5/2 is the non-Abelian, very well-known Morley system. But here I just assume nu equals half and calculating some of the beta answer calculations. So in fact, nu equals half is just bit not necessary, and maybe please focus on this nu equals 1/3.
What is the anion of nu equals half? What's it considered?
Nu equals 1/2. In this case, I assume that there is a semion. So it means that in after braiding, they might get -1. Something.
So what is the state that you consider for nu equals half? What about exactly?
In fact, this is a calculation of edge calculations. So I just put
No, but the box egg corresponded. You cannot say the egg without the box.
Yeah. There is some. There must be Burke theory, but
So basically, you have 4 candidates for that.
Yes.
One is liquid.
Yeah.
You not consider.
Yeah.
One is Fafin, one is anti-Fafin, and the last is pH Fafin. What's the
In fact, none of this. I'm sorry.
No,
Because what you say is that ground state of the Morley system, but maybe you can think about the bosonic fractional quantum Hall system. Then you can get a half-loop nucleus 1/2. I think this is the system. This, at least the corresponding bulk theory of this nucleus 1/2 is the bosonic fractional quantum Hall system.
So it's bosonic 1/2.
Yeah, bosonic 1/2. Yeah. That's
Color
right.
colors are oh, sorry, the color, I see. This bosonic 1/2.
Yes, yes. In fact, I know there is I know there is maybe some controversies about the bulk theory of the nucleus 1/2. So please do not see this red line. Maybe this most easy thing. I put this 1/2 because this 1/2 H theory is quite easy. 1/2 H theory is different. I want to emphasize that 1/2 H theory is very different from the H theories of the 5/2. 1/2 H theory is just some bosonic H theory and some semi-ion tunneling, and this can be mapped into the defermionization or something. So this is totally different from 5/2. I'm sorry. I'm sorry for making you confused. Sorry. Yep.
Just a question about experiment. So
Yes.
you show on the paper where you measure entropy, residual entropy for 2-channel
Yes.
problem. But device is made also for 3 channels.
Yeah.
So are you doing this experiment because there should be Z3 parafermions?
Yeah.
It's even more interesting.
Yeah. First of all, I'm not experimentalist, as you know, so I didn't do this. And experimental guys, up to my knowledge, they try to measure it. And since I didn't mention about 3-channel Kondo system, maybe there is some result on the 3-channel Kondo system. In this case, they approach it to the log of Boulder ratio one, which is more exotic one. And as a theorist, we predict it, but I don't know about the experimental progress up to now. Up to my knowledge, they tried to, but they didn't get it now.
So,
Yep.
So in the case of this single channel Kondo, there is
Yes.
concept of Kondo temperature.
Yeah. There is concept.
Here also you have the concept of Kondo temperature.
Yes, of course.
And what happens there? Something special? No.
If you lower, so if your temperature is much larger than the Kondo temperature, then it means that this large dot or this impurity is decoupled to the lid, and you finally get the log 2, trivial one.
So then you don't see anything.
Yes. You only see the log 2.
Decoupled
Yeah, decoupled, almost decoupled.
at large temperature.
Yeah, large temperatures.
Why is that? Can you give an intuitive explanation?
Because they can populate all the state. So first of all, we can say using some RG equations that this Kondo interaction is relevant. So if you lower temperature, then more Kondo strength, and goes to a fixed point. It means that otherwise, if you larger the temperature, then this Kondo strength becomes weaker, and finally irrelevant. So there is the log 2 of the impurity and some entropy of the lead.
The temperature is measured where? In the leads or on the dot, or where do you define the temperature?
Temperature is
You said temperature, high temperature.
Yes.
What?
Temperature of the temperature of the system, in fact,
The entire system.
entire system, because there is a experimental systems. System, it's so far. So there is a,
Yeah, the whole system. The whole system.
whole system. Yeah, they
Why
make
should at high temperature? Why should the dot be decoupled? I mean, it sounds strange, right? Does it mean that at high temperatures you basically have no transport through the dot anymore?
weak transport. There is only weak transport. The means that this tunneling strength is so if you measure the conductance through this dot or some
I see.
then conductance goes lower as you lower the temperature, larger the temperature.
But I wouldn't call that a decouple.
Yes, in some sense it is decoupled, but in some sense not.
So this is the consequence of energy flow.
Yeah, energy flow. Yeah.
Are there experiments on this Majorana fermion, which sits on one of the edges of extended quasi-1D system? Are there experiments which have been finding such states, just in general, not related to your focus, but just in general? Is there any experiment? Many, right?
Since the 2020, that many experimental groups do the experiment was still no smoking. I mean, nobody believes that.
Many means there are none. Any equals zero.
There's
No, the answer is not. Okay, there are many groups who try to find.
Any other questions from the audience? Seems not, so then let us end to.
Yeah, thank you very much.